Determining the rated voltage of a capacitor solely from its physical appearance is generally not possible. Additional information or testing is needed to ascertain its voltage rating. One possible approach involves checking for color coding. Some capacitors use color bands to indicate their voltage rating. Referencing a capacitor color code chart may help decipher the bands and determine the voltage. Secondly, measure the capacitance of the capacitor using a multimeter set to capacitance mode. Generally, higher capacitance values correspond to lower rated voltages, but this is not a definitive method. Thirdly, contacting the manufacturer is another avenue. The manufacturer's website or customer support may provide specifications for the specific capacitor model. If these methods are not feasible, estimating the rated voltage based on physical characteristics and markings can be attempted. Larger capacitors typically have higher voltage ratings compared to smaller ones. Also, any markings other than the capacitance value may offer a clue. For example, the letter W often indicates a voltage rating in volts. When using a multimeter to measure capacitance, ensure the capacitor is discharged before connecting the meter to avoid damaging the meter or the capacitor. Capacitors store electrical energy, and measuring a charged capacitor can lead to inaccurate readings or damage. The color codes on capacitors typically follow established standards like EIA or JIS. These standards define specific colors and their corresponding numerical values, which are then used to represent the voltage rating, tolerance, and other parameters. Consult a reliable color code chart to accurately interpret the color bands on the capacitor. When estimating the voltage rating based on size, remember that this is only a rough approximation. The actual voltage rating depends on various factors, including the dielectric material, construction, and intended application of the capacitor. If the capacitor has any alphanumeric markings, research the manufacturer's part numbering system. Manufacturers often use specific codes to indicate the voltage rating, capacitance, tolerance, and other characteristics of their capacitors. Searching online databases or contacting the manufacturer can help decode these markings. Understanding the construction and materials used in the capacitor can provide insights into its voltage rating. For example, ceramic capacitors are generally suitable for high voltage applications, while electrolytic capacitors typically have lower voltage ratings. Examining the capacitor's datasheet or specifications can confirm its voltage rating and other parameters. If you are working with high voltage capacitors, take appropriate safety precautions to avoid electrical shock. Use insulated tools, wear safety glasses, and discharge the capacitor before handling it. The voltage rating of a capacitor indicates the maximum voltage that can be safely applied across its terminals without risking damage or failure. Exceeding the voltage rating can lead to dielectric breakdown, short circuits, and other problems. When selecting a capacitor for a specific application, choose one with a voltage rating that is significantly higher than the expected operating voltage to provide a safety margin. The physical size of a capacitor is influenced by both its capacitance and voltage rating. For a given capacitance value, a higher voltage rating typically requires a larger physical size to accommodate the thicker dielectric material needed to withstand the higher voltage. Conversely, for a given voltage rating, a higher capacitance value typically requires a larger physical size to accommodate the larger electrode area needed to store more charge. The markings on a capacitor may include not only the capacitance and voltage rating, but also other parameters such as tolerance, temperature coefficient, and series resistance. These parameters can affect the capacitor's performance in different applications. The tolerance of a capacitor indicates the allowable variation in its capacitance value. For example, a capacitor with a tolerance of plus or minus 10% may have an actual capacitance value that is 10% higher or lower than its nominal value. The temperature coefficient of a capacitor indicates how its capacitance value changes with temperature. Some capacitors have a positive temperature coefficient, meaning their capacitance increases with temperature, while others have a negative temperature coefficient, meaning their capacitance decreases with temperature. The series resistance of a capacitor is a measure of its internal resistance, which can affect its performance in high-frequency applications. Capacitors with lower series resistance are generally preferred for these applications. When replacing a capacitor in a circuit, it is essential to choose a replacement with the same or higher voltage rating and capacitance value. Using a capacitor with a lower voltage rating can lead to failure, while using a capacitor with a different capacitance value can affect the circuit's performance. The type of dielectric material used in a capacitor affects its performance characteristics, including its voltage rating, temperature coefficient, and frequency response. Common dielectric materials include ceramic, film, electrolytic, and tantalum. Ceramic capacitors are known for their high voltage ratings, low losses, and stability over temperature. Film capacitors are known for their high accuracy, low distortion, and long life. Electrolytic capacitors are known for their high capacitance values and low cost, but they typically have lower voltage ratings and shorter lifespans. Tantalum capacitors are known for their small size, high capacitance values, and stability over temperature. The construction of a capacitor also affects its performance characteristics. Common capacitor constructions include multilayer ceramic, metallized film, and wound foil. Multilayer ceramic capacitors are made by stacking multiple layers of ceramic dielectric material and electrodes. Metallized film capacitors are made by depositing a thin layer of metal on a film dielectric material. Wound foil capacitors are made by winding alternating layers of metal foil and dielectric material. The intended application of a capacitor also influences its design and performance characteristics. For example, capacitors used in power supplies typically require high voltage ratings and low series resistance, while capacitors used in filters typically require high capacitance values and low losses. When selecting a capacitor for a specific application, consider the following factors: voltage rating, capacitance, tolerance, temperature coefficient, series resistance, dielectric material construction, and intended application. Refer to the manufacturer's datasheet or specifications for detailed information about the capacitor's performance characteristics. If you are unsure about the correct capacitor to use in a specific application, consult with a qualified electronics technician or engineer. Improper capacitor selection can lead to circuit malfunction or failure. Always follow proper safety procedures when working with capacitors, especially high voltage capacitors. Capacitors can store electrical energy even when the circuit is turned off, so it is essential to discharge them before handling them. Use a resistor to safely discharge capacitors by connecting it across their terminals. Avoid touching the capacitor terminals directly, as this can result in electrical shock. Store capacitors in a dry, cool place away from direct sunlight and extreme temperatures. Exposure to moisture, heat, or sunlight can damage capacitors and reduce their lifespan. Regularly inspect capacitors for signs of damage, such as cracks, leaks, or bulging. Replace any damaged capacitors immediately to prevent circuit malfunction or failure. When soldering capacitors into a circuit, use a low wattage soldering iron and avoid overheating the capacitor. Overheating can damage the capacitor and reduce its lifespan. Use appropriate soldering techniques to ensure a good electrical connection between the capacitor leads and the circuit board. Clean the circuit board after soldering to remove any flux residue which can corrode the capacitor leads over time. The lifespan of a capacitor depends on various factors, including its voltage rating, operating temperature, and the type of dielectric material used. Electrolytic capacitors typically have shorter lifespans than ceramic or film capacitors, especially when operated at high temperatures. You can extend the lifespan of electrolytic capacitors by directing their voltage rating and operating them at lower temperatures. Regularly replace electrolytic capacitors in critical applications to prevent circuit malfunction or failure due to capacitor aging. Capacitor aging is a process in which the capacitor's capacitance value gradually decreases over time due to changes in the dielectric material. This can affect the circuit's performance and eventually lead to failure. You can monitor capacitor aging by periodically measuring its capacitance value using a multimeter. Replace the capacitor if its capacitance value has decreased significantly from its nominal value. The equivalent series inductance, or SL, of a capacitor is the inductance caused by the capacitor's internal construction, primarily the leads and internal connections. ESL can affect the capacitor's performance in high-frequency applications, as it can cause the capacitor to behave like an inductor at high frequencies. Capacitors with lower ESL are generally preferred for high-frequency applications. The equivalent series resistance, or SR, of a capacitor is the resistance caused by the capacitor's internal construction, primarily the dielectric material and electrodes. ESR can affect the capacitor's performance in high-frequency applications, as it can cause the capacitor to dissipate power as heat. Capacitors with lower ESR are generally preferred for high-frequency applications. The dissipation factor, or dF, of a capacitor is a measure of its energy loss. dF is the ratio of the energy dissipated in the capacitor to the energy stored in the capacitor. Capacitors with lower dF are generally preferred for high-frequency applications. The quality factor, or Q, of a capacitor is a measure of its energy storage efficiency. Q is the reciprocal of the dissipation factor. Capacitors with high Q are generally preferred for high-frequency applications. The self-resonant frequency, or SRF, of a capacitor is the frequency at which the capacitor's impedance is at its minimum. At frequencies above the SRF, the capacitor behaves like an inductor. Capacitors with higher SRF are generally preferred for high-frequency applications. The impedance of a capacitor is its opposition to the flow of alternating current. The impedance of a capacitor decreases with increasing frequency. The reactance of a capacitor is its opposition to the change in voltage. The reactance of a capacitor decreases with increasing frequency. The phase angle of a capacitor is the angle between the voltage and current waveforms. The phase angle of an ideal capacitor is 90 degrees. Real capacitors have a phase angle that is slightly less than 90 degrees due to the effects of ESR and ESL. The dielectric absorption, or DA, of a capacitor is its tendency to absorb and release electrical energy. DA can affect the accuracy of circuits that use capacitors for timing or filtering. Capacitors with low dA are generally preferred for these applications. The leakage current of a capacitor is the small amount of current that flows through the dielectric material. Leakage current can affect the performance of circuits that require low current consumption. Capacitors with lower leakage current are generally preferred for these applications. The dielectric strength of a capacitor is its ability to withstand high voltages without breaking down. Capacitors with higher dielectric strength are generally preferred for high voltage applications. The insulation resistance of a capacitor is a measure of its ability to prevent current from flowing through the dielectric material. Capacitors with higher insulation resistance are generally preferred for applications that require high impedance. The surface mount technology, or SMT capacitors, are designed for mounting directly onto the surface of a printed circuit board. SMT capacitors are smaller and lighter than through-hole capacitors, and they offer improved performance in high-frequency applications. Through-hole capacitors have leads that are inserted through holes in a printed circuit board and soldered on the opposite side. Through-hole capacitors are larger and heavier than SMT capacitors, but they are easier to handle and solder. The ceramic multilayer capacitor, or MLCC, is a type of SMT capacitor that is made by stacking multiple layers of ceramic dielectric material and electrodes. MLCCs are known for their small size, high capacitance values, and stability over temperature. The tantalum capacitor is a type of electrolytic capacitor that uses tantalum pentoxide as the dielectric material. Tantalum capacitors are known for their small size, high capacitance values, and stability over temperature, but they are more expensive than aluminum electrolytic capacitors. The aluminum electrolytic capacitor is a type of electrolytic capacitor that uses aluminum oxide as the dielectric material. Aluminum electrolytic capacitors are known for their high capacitance values and low cost, but they have lower voltage ratings and shorter lifespans than tantalum capacitors. The film capacitor is a type of capacitor that uses a thin film of plastic as the dielectric material. Film capacitors are known for their high accuracy, low distortion, and long life, but they are larger and more expensive than ceramic or electrolytic capacitors. The supercapacitor is a type of capacitor that stores energy electrostatically using a double layer of ions at the interface between an electrode and an electrolyte. Supercapacitors have much higher capacitance values than traditional capacitors, but they have lower voltage ratings. Supercapacitors are used in a variety of applications, including energy storage, power backup, and hybrid vehicles.